Good. So I want to continue on to the proof of the main theorem, right? That tells you that the new definition of new definition of additive convolution in general is the original one. So I'm going to need two more. I told you we need 3 theorems for linear algebra or matrix analysis. Let me give you the other 2. But first, a little bit of notation. So say you have a set of integers. We are going to have sets of integers. Essentially indices of the rows and columns, but so maybe this is S1 to Sk. So we are going to assume that they are ordered according to the indices. Okay, so S1 is at most S2. So whenever we see a set S1, S2, and so forth, implicitly know that S1 is smaller or equal than S2 and so forth. That's one thing. And the second thing is that if you give me a set of indices W, right, so W is a subset of K. I'm still in this context where I have a set of S1 up to Sk. When I'm denoting by Ws, this is a subset of S in which I'm only taking the SIs where the index I is in W. Okay? I have an example here, maybe? I swear I had an example, but it's not here anymore. Whatever. Right, so like 1 S is S1. It's a weird notation a little bit. But a set applied to a set with the right type. So the S is S1 up to Sk, and W is a subset of K. Then W just fish out those elements from S that you want. And lastly, just, a little bit more notation, last notation. This kind of one norm of S is just going to be the sum of the elements from S. Everything is anyhow positive, so it really is the one norm. Okay, so the 2 theorems that I told you that we need, 2 extra theorems, are the following. The first one actually explains also why it's more natural to consider polynomials the way we consider them in this unit, for the purpose of this unit, not in general. So let's say that A is a D-dimensional matrix. I switch back to D, with a characteristic polynomial that looks like that. All right, so again, it's the same way we wrote it before. So sigma k is what we called AK before, A sub k, but I want to give it a name like that so that I remember the matrix itself, not just by the fact that it's a lower and capital of the same letter. So you write it as we wrote it before. Then it turns out that AK has a very nice interpretation in terms of minors of A. Right? It's, you can ask how should you interpret the coefficient of some power in the characteristic polynomial? Then this theorem tells you, the answers your question. It tells you that the corresponding coefficient is the sum of all minors, diagonal minors, SS, you see, of size K. And examples of that, at least the extreme cases. That, for example, when K is 0, so when K is 0, it means you look at X to the D, the coefficient should be 1 because it's a characteristic polynomial. And it's indeed 1 because when K equals 0, you look at only subsets of size 0. And we said that in that case, the minor is defined to be 1. When K equals 1, right? What is the coefficient of X to the D minus 1? Well, it's the trace, essentially, if you remember that. Or maybe minus the trace, but it's minus the trace. And indeed, you can see it here because when K equals 1, you're looking at sigma 1. And sigma 1 is, you take all diagonal minors of size 1, which is exactly the diagonal entries, right? The minor of an entry is just the entry. It's not the absolute value or something like that. So indeed, sigma 1 is the trace. And when K equals D, it should be the determinant minus up to a sign, which now could depend on D, it's minus 1 to the D. And indeed, when K equals D, you need to go over all subsets of size, which is the same size as the matrix. Then there is only one subset, and you take that minor, which is exactly the determinant of the matrix. Okay, so this theorem generalizes that to all of the coefficients, not just the 3 extreme coefficients that you probably remembered. Okay, so that's one thing. I think that's a nice theorem to just know in general. Secondly, a theorem that's useful to know in general is the following. So you can ask, if I have two matrices A and B, D by D matrices, and I ask what's the ST minor of their sum, then it should appear at some point, right? Because we're talking about sums of matrices. Then what is it? How can you express it in terms of minors of the individual matrices? Then it turns out that if the sets S of S and T are size K, right? That's what's written here. Then what you should do is the following. You should go over all sets of all numbers you should go from I equals 0 to K, and then you go over all subsets of 1 to K of size I. And then there is this sign that depends on the elements that appears in U and V. But what you should do is you should take the indices from S according to U, indices from V according to T, and take the corresponding minor. And same from B. For B, you need to take the indices that you didn't do. So this is U complement, right? Complement to respect to K. So you take the elements, the indexes you didn't take from S here, and same here. So with this, we're actually ready to prove the theorem. Well, actually, we need the lemma before. So here's the lemma. So say you have an n by n matrix B, and R is an m by n minor orthogonal matrix. M is at most n. Then for every S and T of size K, what I claim is that this equality holds. Namely, if you essentially, if you take B and you conjugate it by R, which is a minor orthogonal, any minor orthogonal family distribution, but you average over R and take the ST minor, then R scrambles B so well so that the only thing that survives is the S equal T minor, namely SS. And in such case, you get a kind of a normalized version of the K coefficient of B. Okay, so let's see the proof. So on the left-hand side, we have this thing, and then we are going to apply Cauchy-Binet twice, right? So we are introducing both X and Y, and we are summing, we switch expectation and summation order, but we are summing over all X and Y, R S X, B X Y, R conjugate YT. And because kind of ignoring this B and put it aside, because R is minor orthogonal, this thing boils down to S has to be equal to T, X has to be equal to Y, and then you have this factor. Okay, so the fact that S has to equal to T sits here. The fact that X equals to Y just collapses this sum to one summand. And then you sum over BXX because X equals to Y. Okay. And this, by the theorem that I stated, is exactly the K coefficient of the characteristic phenomenon of B. That's it. Okay, and with this, we're actually ready finally to prove the main theorem. So let me restate it in per coefficient. So rather than as the characteristic polynomial. So this is a reformulation of theorem 1, but it's the same thing. So let's say that A is a D by D matrix and R is a D by D minor orthogonal matrix distribution. Then the expectation over R of the K coefficient of this thing, right? Before we looked at the characteristic polynomial and said the expectation of the characteristic polynomial is something, but now we're just looking per coefficient. So it's the same thing. And the expectation is in coefficient space after all. So the expectation over R of the K coefficient of the sum is exactly what I claimed in the theorem. It should be, right? This was like AI, and this was like BJ, where I plus J equals K and so forth, but it was this thing. And so let's go over the proof. So on the left-hand side, you have this thing, and now we are going to use the theorem that we mentioned, which expresses the Cave coefficient as the sum of a diagonal with diagonal minors of the corresponding size k, because we are looking at the Cave coefficient, so it's size k. And now we are going to use this kind of long theorem that tells you how is the minor of a sum looks like, right? So this sum is that sum, and then you should sum I from 0 up to k, if you remember, and you go over all subsets of size I of k. You have this sign, and then you do the following. You fish out the elements of S according to U that are indexed in U. U runs over all subsets, but and same for V here. And you do the same for the other matrix, and the other matrix is RB R conjugate. And I kind of also pushed the expectation as far as I could, so I put it here. Okay. This was true per R, but there is an expectation over it, so I pushed it. Now, by the previous lemma that we just had, this thing is it's usually 0. It's not 0 exactly when this set is that set, right? Which implies that U equals V, right? These are the indices of different numbers, so it means that U equals V. And when it's not 0, it's this number. That's a previous lemma. So let's see. So, but let's also change order of summation. So here we sum from I equals 0 to k, and then we take this expression and put it here. It only depends on I and k and b, so these are fixed. And then we sum over all s and over all u. U equals to v now because of this, so we don't have to worry about v. And then this sign goes away because u equals v, so just 1. And then you have us rather than vs because u equals v. So this star I claim equals to this thing, right? Because, you know, what you're doing here is you sum over minors, but you overcount. You sum over minors of a of size I, but the way you do it is you first choose a set S of size k inside 1 to D, and then you choose a subset of I in that set, and you take the minor of the set that you ended up with. So there is an overcounting here, but it's completely symmetric. So what I claim is that, there should be a sum here, sorry, is that you take every set of size I of k exactly D minus I choose k minus I times. And indeed, you know, if you fix a set V here, and you ask how many times in the sum, or maybe it here, how many times do you sum it? It is counted exactly 1 time for every S that contains V, right? So if S contains V, then there is a choice of U, and exactly one choice of U that will produce, that SU couple will produce V. And if S doesn't contain V, then no subset of it of size I will give you back V. Right, so you count V exactly once for every set S that contains V. And then you can ask, you know, what you should ask, how many sets S of 1 up to D of size K contains V? Well, you know, V is of size I, so, you know, you need to complement V to this set S and ask how many ways you have to do that. Well, you just have to add or to, you know, take a union of K minus I other elements out of the D minus I elements that are not already in V. And that's the reason for this. Okay, so plugging it to the calculation that we had. So this is from the previous page. Plug in what we just did here. So replacing that with this, you get this, and then by the theorem that we stated, this is precisely sigma I of A. which concludes the proof. Lastly, I want to end up with two corollaries of the theorem. The first one is lemma d that I owed you from the previous unit, and it's same unit, previous lecture. And I mean, it will essentially complete the proof of the finite R transform theorem, but for one thing, the underlying assumption that if you take two real-rooted polynomials and take the additive convolution, it gives you a real-rooted polynomial. It's not clear, not from the original definition that we had, nor from the current, more general definition. That will actually, I mean, also these definitions are like more general, and so maybe you shouldn't expect that. That one thing that I owe you will come in the the next unit about, or the next unit about interlacing. The next unit is about quadrature. So, but other than that, we concluded the proof of the R transform. So that's the first thing we'll prove. And the second thing is this theorem that I was telling you about, kind of in passing, of how does the additive free convolution looks like in terms of the roots rather than the coefficients. Okay. But let's start with lemma d. So lemma d, just let me remind you, it tells you that if you have a degree at most d polynomial p, and you have a degree at most d minus 1 polynomial q, then the diff additive convolution of them is related to the d minus 4th additive convolution of q, which is always valid. Q is of degree at most d minus 1, and a normalized version of the derivative of p. Okay, we use that in the proof. Okay, good. So that also relates, we talked a little bit about what happens with the C and D different additive convolutions. So from here you can get some relations. Okay, so let's just do the proof. It's a one-liner essentially. So first of all, let's just recall, we are going to use this lemma that expressed the additive convolution in terms of the derivatives. It makes sense to look at this definition because we have derivatives here. So that's what we proved in the previous lemma. Okay, so that's the left-hand side. On the right-hand side, let's also use the lemma. It looks like that. Right now it's 1 over d minus 1 factorial because we're looking at the d minus 1, d minus 4th additive convolution. And then we sum from 0 up to d minus 1, and then that k, and we take the kth derivative of the polynomial that we have, which is, 1 over d times the derivative of p of x, times the derivative complementing to d minus 1, complementing k to d minus 1 of q and evaluating at 0. Now, the point is that, these two derivatives, I mean, the derivative of derivative is a higher derivative, so it's d to the k plus 1. The 1 over d goes and plays along with the 1 over d minus 1 factorial, and that's it. And now we're just going to renumber that. So instead of going from 0 to d minus 1, let's go from 1 to d, just define j to be k plus 1. So this is the jth derivative of p of x times the d minus j derivatives of q applied to 0, right? Because this is like, you can write it like that, and that's j. And it's almost what we have here, besides for the fact that j is k, but that's fine. The only difference is that here it starts from 0, and here we start the sum from 1. But that's okay, right? Because when j is 0, it means that you take the diff derivative of q, which is degree d minus 1 polynomial at most. So it's anyhow 0, and so we can safely put a 0 here, and then we get what we want. Okay, so this is the proof of lemma d. You can probably prove it using the old definition, like more restricted definition, but it kind of readily follows from this definition, so why not? And the last theorem I want to talk about in this unit is this corollary, really cool corollary that tells you how additive free convolution looks like in terms of roots. So now let's look again. So let's look at two polynomials, but now write them in terms of the roots. So let's say p of x is x minus ai. The a 0 up to a d are the roots, and maybe it should be from 1 because I want a degree d polynomial, not a degree d plus 1 polynomial. Yes. So let's say that P is, has A1 up to AD as its roots, and Q has B1 up to BD as its roots. Then what I claim is that, what I claim is that the additive free convolution of them is the following. So you take the expectation over all permutations of 1 to D. Okay, and then you look at this polynomial, which has it as its roots AK plus B sigma K. Right, so put differently, you take the expectation, you take a random sigma, and then you look at the polynomial whose roots are, according to that permutation, AK plus B sigma K. So in a sense, like you see the roots completely get scrambled like that. And the additive translates to the fact that you add them up. I think it's a beautiful result. Okay, and to prove that, so let's see. So let's take, we're actually going to use the previous definition, but with minor orthogonality. So let's construct two matrices, diagonal matrices A and B. On their diagonal, we are going to put the corresponding roots. And by our main result, we know that the additive free convolution is the one corresponding to the characteristic polynomial of these matrices is equal to this expectation for any distribution R which is minor orthogonal. It doesn't have to take R. You can take any minor orthogonal distribution that you want. In particular, we're just going to take the other distribution, namely that we know of, which is sign permutation matrices. Okay, so what is a sign permutation matrix, right? R is E chi times pi sigma. It was P pi from before, but P sigma here, where sigma is a permutation, is a random permutation, and chi is a random signing, and they are independent. Then let's look at a particular, so I'm moving here, I'm looking at a particular element here, before taking the expectation. So what is this? So that's just the determinant of xi minus a minus rbr transpose. R is real valued. And what is R, right? It's E chi times P sigma. So that's its transpose. And what happens is now is that P sigma and P sigma, sorry, not P sigma, E chi and E chi transpose get cancelled. It's just a diagonal 1 plus minus 1. So it multiplies, gets a 1. And you are left with this thing. And the point here that from here, it's really, these are just like diagonal matrices. So what really happens here is that, you know, A stays A, but B, the diagonal element just flip according to sigma. So the determinant of this diagonal matrix is precisely the product of this product, right? Of the diagonals entries. So that's per element in the expectation. And so this thing, which is the expectation over that, is the expectation over all sigma, because it doesn't matter anymore of this thing, which is what we wanted to prove. Good. So we are done with the R transform theorem. Again, but for the fact that I still owe you a proof that real rootedness is preserved under additive free convolution. The plan for the rest of the course, which is just about to end, is doing quadrature. So we are going to prove a quadrature result, namely that the expectation over R is the same as the expectation over permutations, even though permutations are not minor orthogonal. But in a certain restriction that will be okay for us. That's a fairly short unit. And then in the following unit, last unit, one before last unit, we are going to talk about interlacing, which will enable us to argue about one permutation given something we know about expectation. And we know about expectation because of the quadrature. And then in the final unit, which is be extremely short, it's a corollary, we are going to prove the existence of one-sided Ramanujan graphs. Right? So it's essentially Ramanujan graphs, but we're only going to bound lambda 2 rather than lambda 2 and lambda n simultaneously.